Let us explore recursively enumerable languages, also known as semi-decidable languages, and some of their important properties. These languages are closely related to Turing machines. Formally, a language L is recursively enumerable if there exists a Turing machine M, such that L is equal to L of M. In simpler terms, a language is recursively enumerable if there's a Turing machine that can recognize it. We denote this as L belongs to RE, where RE stands for recursively enumerable languages. Recursively enumerable languages have two key characteristics related to how a Turing machine behaves when processing strings. First, for strings that are in the language L, the Turing machine will halt and accept them. Second, for strings that are not in the language L, the Turing machine might loop forever, or halt and reject them. The important point is that it doesn't necessarily halt for strings not in the language. It's important to distinguish between semi-decidable and decidable languages. For decidable languages, also known as recursive languages, the Turing machine always halts, either accepting or rejecting the input string. In contrast, for semi-decidable languages or RE languages, the Turing machine may not halt. It either accepts or loops indefinitely. Also, the set of recursive languages R is a subset of recursively enumerable languages, RE. There is a fundamental enumeration property associated with recursively enumerable languages. A language L is recursively enumerable if and only if L can be enumerated by some algorithm. An enumerator algorithm systematically generates and outputs all the strings in language L. Recursively enumerable languages exhibit specific closure properties under certain operations. RE languages are closed under union, which means if we take the union of two RE languages, the resulting language is also RE. Similarly, RE languages are closed under concatenation and the clean star operation. However, RE languages are not closed under intersection, complement, or difference. Applying these operations to RE languages might result in a language that is not recursively enumerable. Rice's theorem is a fundamental result in the theory of computation. It states that all non-trivial properties of recursively enumerable languages are undecidable. A non-trivial property is one that is neither always true nor always false for all RE languages. A corollary of Rice's theorem is that we cannot determine if language L1 is equal to language L2 for two RE languages. In other words, there is no algorithm to decide whether two Turing machines recognize the same language. A classic example of a recursively enumerable language is the halting problem. ATM, which is the set of all Turing machines and inputs W such that M accepts W, is RE but not recursive. This has practical implications for program verification. We cannot always determine if programs terminate. This is a fundamental limitation in computer science. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.